Let's now resume. Let's try this problem. I hope you can answer 4 problems in this video. Let's uh, let's do it. So, compressor in a fridge takes R134A compressor. Oh wait, compressor. This is what a compressor looks like. And for your information, this is what a turbine looks like. Sorry. No. Yeah, this is correct. So compressor, we have inlet, outlet. This is open system because we have a thermodynamic device. Steady state or not? Let's see. Let's write the given first, no? And required. So for the given, compressor in refrigerator takes refrigerant R134A in at 100 kilopascal, negative 20 degrees Celsius, compressed to 1 megapascal, 40 degrees Celsius. So we are given room temperature, 20 degrees Celsius. Required is the compressor work minimum. This is, in other words, the ideal reversible work or isentropic work. Okay. Law of conservation of mass, M1 is M2 is M. Steady state. Assumptions: negligible kinetic energy, negligible potential energy. What else? We'll see. Right now we don't really. Okay, FLT. This is open system, so delta H equals Q plus W. No? So at state I, 100 kilopascal. Is there any other information? Find minimum compressor work. Let's go to R134A. Do we have pressure? We do. 1 megapascal is 1000 kilopascal. Shaft work is not equal to 0 since this device is a compressor. No? So assume reversibility. In that case, we have also SLT. Entropy is equal to integral dq over t plus sgen. But since reversible process, Sg equals 0. So this one is going to be 0. So we have Q and then T and then delta S. Q reversible is T delta S. In that case, H2, H1, the Q here could be the Q rev and then work. Okay. Let's make this, sorry. Let's make this E, let's make this I. H sub I. So 100 R134A, no? 100 kilopascal, negative 20 degrees Celsius. 387.22. Oh, wait. Q rev is then T sub O S2 minus S1. Let's make it S sub E, S sub I. S sub I is (100 kilopascal, negative 20, 1.7665. State E, exit is 1000 kilopascal, 40 degrees Celsius. $420.25, that's gonna be H sub E. S sub E, 1.7148. Let me see if this is gonna get the right answer. So we have this. We don't know the mass. How do we identify the mass? We don't even have the volume. Oh yeah, don't forget this. So apparently we don't need a mass for some reason. Wow. Yeah, we were able to get the idea, but what the hell? Minimum compressor work. It's a capital letter, no? So I guess that's another rule. There's so many exemptions, bro. It's crazy. Thermodynamics is crazy. I guess if there is no QRev, then obviously you're left with capital work. Then there has to be an M. But that's not the case right now. We have a small q rev, no? Specific. Wait. Minimum compressor work. Minimum maximum work. Specific work. Okay, I think that's a misconception. This is wait. What the There are so many exemptions, bro. It's crazy. It is crazy. Okay, just wait, is minimum compressor, oh, what the so I'm asking if the minimum compressor work has the same unit as specific work, that is kilojoule per kilogram. They're not the same according to the internet. What the it's just in this case, yeah, let's just put it together. Wait, is it negative 20? No, no, no. Why did I put a minus sign? That's misleading. Handwriting is really important. Proper handwriting, no? Okay. 48.19 kilojoules per kilogram. That's the answer. Let's go to the next practice problem. So, wait. Let's say we have a reversible isothermal expander. I think this is how they draw it. Same, essentially it's very similar, no, to a turbine. We have inlet, sorry. We have exit, stream. Reversible isothermal, so dt equals 0. Yeah. expander is basically a turbine with heat transfer. Has an inlet flow of CO2 at 3 megapascals, 40 degrees Celsius, and an exit flow of 1 megapascal, 40 degrees Celsius. This is our given. Required. Find the specific heat transfer. Specific heat transfer. So small q. This is not total heat transfer, no? Or just simply heat transfer. It's specific. So small q. From the entropy equation. Okay, so SLT is obviously going to be involved here. And the specific work. So small w. From the energy equation. Obviously that's going to be involved. Assuming ideal gas. So these are the given, no? Let's start first with LCM. Then assumptions. Ideal gas, dt equals 0. Is the process steady state or transient state? The process is steady state, no? Because there is no mention of accumulation. In the FLT, this is open system. We have a thermodynamic device, the expander, which has shaft work, no? So work is not equal to 0. So delta entropy equals Q plus W. Is the process adiabatic? No. So Q is not 0, no? What are we looking for again? Small q, small w. Okay. Let's make it small. Then here, H2 minus H1. You don't have to put a mass anymore multiplied to it because what's in the left, we only have Q and W, no? Specific heat. They're not capitalized. They're not total heat and total work. Okay? For SLT, delta S equals integral dq over t plus S generation, entropy generation. Since we are assuming, if we are going to assume ideal gas, so this is both reversible and isothermal, no? So isothermal is already here. But when we say reversible, that means we summon the entropy balance, no? In that case, in reversible process, entropy generation is 0. So we're gonna flag this as 0. Okay. Q over T equal to delta S. T delta S equal to Q. This is gonna be Q reversible now. Let's see. Let's combine the equations. H2 minus H1 equal to T S2 minus S1 plus W. So since the process is isothermal, same temperature, I guess that's just the T here. No? We have information on both inlet and exit stream. So let's find what's our substance? CO2. Is CO2 in our thermodynamic table? Yes, it is. So we do, although it says here that we assume ideal gas, that's not the reason. The reason for that is not because the substance is not in the thermodynamic Sontag table. No? It's just explicitly stated by the problem that we assume the gas ideal. So, state inlet 3000 kPa, 40 degrees Celsius. Let's find that. CO2. CO2, 3000 kPa. Superheated carbon dioxide, no, at this point. 40 degrees Celsius at, okay, we're gonna look for HNS. 378.55. One 1.4104 kilojoule per kilogram Kelvin. Okay, that's for state inlet. For state exit, 1000, no? 40 degrees Celsius. I won't write the unit anymore. It's pretty understandable at this point. HE 398.05 minus 378.55 equals 40. Don't forget this is in Kelvin, so temperature should be also in Kelvin, no? So plus 273.15, then times quantity 1.6633 minus 1.4104. Okay. Plus W. Shift solve, no? At this point, we're looking for work. But this note, remember this one is Q rev, no? We'll calculate that in a separate computation. For now, just shift solve. 398.05 minus 378.55 equal to 40 plus 273.15 times quantity 1.6633 minus 1.4104 plus x. Shift solve. Our work is a negative value. That means work input. Yeah, input. Sorry, output. Work output. I made a mistake. $59.70. What's the unit? Kilojoule per kilogram. Specific work, no? That's what we're looking for. How about oh yeah, we're gonna find the Q reversible. This temperature part, yeah. Temperature and the change in entropy. In that case, it's 79.20. Is it the same unit? Yep. Kilojoules per kilogram. Positive, so this is heat gain, no? Heat gain. Let's check the solution. reversible isothermal expander. Hmm. I didn't get the right answers. We are told to assume gas ideal, no? So I think this is what we were supposed to do. We forwards to what function? The difference in entropy. What the? It's actually pretty crazy, bro. What the freak? For ideal gas, Q reversible. Since reversible is a condition in ideal gas scenario, T delta S is gonna be Cp dt over T minus R dP over P. Yeah. In other words, T equals Cp ln T2 over T1 minus R ln P2 over P1. But we need to derive this. Frick. VdP delta H minus VdP TdS. Always this, always this. Pain in the ass. Okay, let's start deriving. So, so since also conditions for ideal gas, specific volume, let's go back to PV equals RT. V over N, specific volume, molar volume rather, RT over P, no? So therefore, that's the one here. So, also aside from that, what else? Ah, okay. Got it. Delta H is Cp dt, no? These are also conditions for ideal gas, so take note. This one eventually later will get this equation. In the exam, you won't be given any points if you just wrote the formula. You have to show the derivation. No? So Cp dt minus RT over P dP. Delta S equal to Cp dt over T minus R dP over P. There you go. That's how we got this. As in this one only, only this part, not this. This one is the delta S, delta S. I hope you see the vision. Okay, so ds equals Cp ln T2 over T1 minus R ln P2 over P1. So what happens after that? What's our substance again? CO2. We're gonna look at the thermodynamic Sontag table. Go to page 760. Page 760. The specific gas constant for carbon dioxide 0.1889, and then its specific heat capacity at constant pressure is 0.842. So 0.842 ln. Wait, do we know temperature and pressure? Yes, indeed, we do. Hold up. Temperature, isothermal, no? Isothermal process ba? Yeah, isothermal. So 40 over 40 minus R. R is 0.1889. Ln P2, 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 P2. 1 over, okay. 1 over 3. Yeah. I hope this works. Zero point 0.2075. Let's already multiply it by the temperature. $64.99. Yes, we got it. We got it. We got it. Nice. Okay. So just that. Q is equal to T delta S, no? So 40 plus 273.15 times this whole thing. Let's make it small. Is equal to 64.99 kilojoules per kilogram. Okay, let's now find the specific work. So basically this whole thing is as. This is our realization. So instead of reading the tables, we come up with this formula, no? For ideal gas. I hope there's a compilation for all of those formulas concerning ideal gas. That also includes the one earlier, involving finding the ratio of pipe diameters, no? P and then, wait, M over M RT PV, the P d over dt V equal to M, d over dt M, and then R specific, and then times T. R specific being R divided by the molar mass. In that case, this is gonna be that, and then there you go, and then mass flow rate equals to, so we're in this one, a times velocity, and we're in also is density, a velocity over specific volume. No, you just have to memorize those things. And then R spec T, wherein constants. By the way, this is not part of the solution of our problem right now. I'm just compiling, reminiscing something else where gas is ideal, so we don't look at the thermodynamic tables in Sontag, no? So R spec, also the temperature, because the process is isothermal in that problem. Also mentioned that the velocities are constant. So P1, A1 equal to P2, A2, such that A2 over A1, or rather 2 being the exit and 1 being the inlet, equals dE over dI raised to 2 equals Pi over Pe, such that the ratio of the pipe diameters is just simply dE over dI. Okay. This is his final answer already. Okay, so after that, now work is what? Let's just go here. 64.99. HE minus HI. Where do we find HE minus HI? Shoot. I wasn't able to make another realization. Isothermal. Wow. Another thing. Delta H is equal to Cp dt, no? For ideal gas. Since isothermal, so 0, delta H is 0. Therefore, So I think that's another realization. For ideal gas, change in enthalpy is 0. So in the energy balance, negative W is equal to Q rev. Wow! Freaking intelligent, bro. Oh yeah, don't forget, in this kind of yeah, sounds about right. Except that the exit state should be here. There you go. Don't forget about those as well. So in the previous problems, these problems, we did not assume gas ideal, no? Only starting at problem 5, um, and here in problem 8. Is problem 7 gas ideal? No, we only assumed reversibility for the reason that uh, shaft work is involved. So, mhm. How about condenser? Number 6. No, we did not assume gas ideal here, or we are not told to assume gas ideal. Although we used this, even though assumption wasn't ideal gas, um, I think also for incompressible liquid such as lake water, that also we can use this formula. Okay, I think that's enough reminiscing. Let's go back. Let's try this problem. So, how long is this video? 50 minutes. Okay. I need more time to review. Okay, given. Flowing in a pipe, connected to a pipe, valve evacuated tank. Okay, we have this kind of scenario now. Steam at a pressure of 1.4 megapascal and the temperature of 300 degrees Celsius is flowing in a pipe. Connected to this pipe through a valve is an evacuated tank. Evacuated, in easier terms, empty. No? The valve is opened and the tank fills with steam. Until the pressure is 1.4 megapascal. Then the valve is closed. The process takes place adiabatically. Okay, let me just required LCM assumption. So adiabatic, what else? KE and, are we good? KE negligible as well as PE. We are required to determine the final temperature of the steam. Steam, this one. So again, this is state inlet. This one is state 2. State 1. State exit right there. Okay, so what do we do? FLT. Is this... Wait, no. Is this process open system or closed system? We have an incoming stream. We have also an exit stream, but there is no... technically, we have a state exit, but there is no output stream. We have a state 1 and state 2. So this is definitely an open system. This is not a rigid vessel, nor is it a piston cylinder assembly example, no? Open system, but what is the state? Steady state or transient state? Notice state I, state E, state 2, state 1. So this is obviously transient state. For a certain time, we open the valve, and for a certain time, we close the valve. So we now have information on accumulation. No? In that case, 1 plus M1 plus Mi equals M2 plus Me. Wherein M1, since initially tank 1 here there is no gas, it's evacuated, no? So M1 is 0. The mass at state 1 is 0. That's what it means. Also, since there is no output stream, we just keep the stuff, the gas inside this tank too. So mass exit is 0 also. Okay, so how do we simplify? M sub I equals M sub 2. That's our law of conservation of mass. Now, FLT. What's our FLT? What is our FLT? Oh, okay. Transient state, no? M2 U2 minus M1 U1 plus. So this is for the control volume. That's the closed system part of the process. And then we have the accounting for the input and output streams, H M-E H-E mehe minus mihi, then equal to Q plus W. Q plus W. Let me just verify if that is the correct. Okay, yeah, we got it right. Yes, sir. Okay, so this is what do you call it again? The streams. No? Okay, so oh yeah, applying this information. This one is then 0. ME is then 0 also. Simplify the FLT. M2 U2 minus mihi equal to Q plus W. Oh yeah, adiabatic, no? So 0. What are we looking for? T2. At state inlet, 1400 kilopascal and 300 degrees Celsius, no? We can find H sub I. We don't have, do we have the volume of the tank? KE and PE are negligible. This is steam. So we'll go back to water. State 2 is just 1400 kilopascal. Okay. I forgot something important. Okay, okay. I lose. Okay, this is another realization. In that case, so in that case, what's the so what do we do now? I think we can find quality. For what purpose? So this is the T2. Let's go to 3040.35 as the internal energy. Okay. I think I get this part now. So at 1400 kilopascal, we're gonna interpolate. So where is this one in between? No? Let me go to the steam table. This is superheated vapor water, 1400 kilopascal. We are looking at the internal energy. So somewhere here. Where is 3000 something, 3040 something? It's in between these two values. This and this. That's between 400, 500 degrees Celsius. Let's write that down. So what temperature at internal energy of 3040.35? Okay. Calculator, menu setup, go to, what's number 6 here? Statistics and then linear regression. 400, 500, 2952.50, 3121.10. Then go to regression, go to x, and then 3040.35. Okay, so T2 is equal to 3040.35 x hat 452.11 degrees Celsius. That is the final temperature. We were able to solve number 9. Okay? I was able to get that part on my own. It was really just this part that I was really stuck at. No? It's just really difficult to realize it unless you're quite used to it already. And I think that's a really important advantage, no, in the exam. Because even though you know the general procedure, like establishing your FLT, your LCM, but at some point you will be stuck for exactly the reasons I'm experiencing right now. So it wasn't my realization that um, in this problem, I would think that shaft work, or if the problem would have shaft work or not, no? That also decides if we have work or not. In this case, work is 0 because shaft work is not involved. Even though this is already transient state, that question still has to be asked, no? I hope that's clear. Let's go now to number 10. Okay, so we're gonna use the same tank. I'm gonna draw it again. Volume this time, so we're given information on the volume of the tank. Initially contain saturated vapor at 350 kilopascal. The valve is then opened. Stream from the line at 1.4 megapascal and 300 degrees Celsius flow into the tank until the pressure is 1.4 MPa. So calculate the mass of the stream that flows into the tank. Steam rather, mass of steam that flows into the tank. This is transient state again because at a certain point we make an accumulation. So in this case, we already have something in the initial tank, so M1 is no longer equal to 0. No? But since we still have no output stream, then ME is equal to 0. Assumptions. So in this case, assumptions. Okay. So we have negligible KE, negligible PE. What else? That's it for now. FLT, transient. Wait, sorry. Okay. FLT we have another assumption. Work is 0 since no shaft work involved. So remove that, we only have heat transfer. Is the heat equal to 0? There is no mention of heat transfer. So I think we can assume that Q is 0 also. Yes, that is a verified... yeah, I was able to memorize that. So no Q. This one will become this. Okay, let's now go to state 1. 350 kPa, saturated vapor. Let's look at the pressure entry and look for the anything that corresponds to saturated vapor. Wait, what's the substance? Steam. So this is going to be the just water, saturated water. Pressure entry 350. Pressure entry. Okay. Specific volume. I think this is going to be useful. Saturated vapor. No? So 0.52425. 52425. So with that information, we know that gas is just expanding everywhere. No? I mean, it's just all over the place within the tank. So it takes up the volume of the tank. So volume of state 1 is also equal to volume of state 2, that being the volume of the tank. Okay? 0.4. We can therefore find the mass 1 of state 1. Okay. So we have M1 already. How about U sub 1? Okay, let's find exactly that. U sub 1, 350 kPa. 2548.92. For state 2, 1.4 MPa. Hmm. very close in finding the answer, actually. This is just another trick that uh, has to be mastered, no? It was intentional that state 2 has no corresponding temperature. As tempting as it can be to just check the pressure entry and just find an answer there, that's not the right way of solving, no? You won't get any points for that. You'll end up with just grace points, and it's something that you don't want, no? Out of 20, you only get like two 2 points max. No one passes if you're only given grace points, no? I'm not gonna push myself. I'm gonna stop here. I might just forget the concept again. So better I learn this again in a few days, no? I have another exam to prepare for. Bye bye.